today we will learn about the electronic spectroscopy of a molecule. So, before starting this electronic spectroscopy of a molecule, let us summarize the vibrational and rotational spectra of a diatomic molecules, whatever we have learned so far. So, basically in case of rotation, we have considered two models, rigid rotator and non-rigid rotator. So, in case of rigid rotator, so diatomic molecule mass M1 M2 and this bond length is R0. So, this it is reduced to one mass problem, one body problem, and this reduced mass is mu equal to M1 M2 by M1 plus M2, and moment of inertia I equal to mu R0 square. Okay. And energy, of course, this this translational motion, whatever energy is half mv square. So, m is replaced by I, moment of inertia, and v is replaced by omega, angular velocity. So, energy is half I omega square is basically p square by 2I. P is not linear momentum, is angular momentum. So, P equal to whatever mv, so m is replaced by I, v is replaced by omega. So, P equal to IV. Okay. So, using quantum mechanics, one can find out the quantized energy of the rotator. So, this Ej that we have seen, this equal to h cross square by 2I. It is just like h cross square by 2m in case of linear motion. In case of angular motion, angular case, so it's h cross square, same is replaced by I. So, 2I j plus 1, and that is in energy if you express in joule. So, this is the expression. Now, we are interested to express this energy in terms of centimeter inverse, means in terms of wave number. So, that is Ej. So, this different notation for E is used. So, Ej equal to h by 8 pi square C I j plus 1. So, this we have written as a constant B. So, B j plus 1, whereas B is this. Okay. So, here we have put I equal to mu r square. So, here basically we are seeing this this B is proportional to 1 by r square. This means if r is higher, so this B will be smaller. So, B is called the rotational constant. Okay. So, rotational constant is very sensitive to the distance between the two atom. If its change is varies with square of the distance r square. Okay. And that we have seen this what will be the spectral lines, what will be the energy or wave number of the spectral lines. So, just transition from j to j plus 1 states. So, this will be 2b j plus 1. So, following the selection rule, del j equal to plus minus 1. So, one can get this spectral lines, rotational spectral lines, and their separation are constant, that is 2b. Okay. So, equispace spectral lines we will see if it is rigid rotator, but in reality generally we found very small number of molecules which behave like rigid rotator, but most of them behave like non-rigid rotator, means during rotation due to centrifugal force. So, this bond length is changed. So, if we consider that one, so that will be basically non-rigid rotator, and in case of non-rigid rotator, so this energy will be corrected by these factors. Okay. So, that is minus d h c j square j plus 1 whole square. Okay. So, in this case the d is called distortion constant due to centrifugal force. Okay. And here k we have written. So, as if we consider the spring mass system, it's the stretching, okay, due to rotation. So, this spring constant, that is basically is k is omega mu omega 0 square. So, mu 0 is natural frequency. So, that you know this mu 0 equal to square root of k by mu. So, so this you will get in terms of wave number. So, this mu 0 bar we have written. So, this will be the k value. Okay. And one can show that using b and omega 0 bar value. So, this d is basically depends on b as well as this omega 0 square. Okay. This is the relation, and in case of this energy of the spectral lines will be this. So, 2b j plus 1, 2b j plus 1 minus 2d j plus 1 cube. So, for lower value of j, this rotational quantum number, so you will get basically you will not get much deviation of spectral line from the spectral line of rigid rotator, but for higher value of j, you see this value, this value 2d j plus 1 cube. So, this will increase for higher value of j. So, so this total value will, this energy of the spectral lines in centimeter inverse. So, that will decrease. Okay. So, whatever the spectral lines we have seen for rigid rotator, so they are equispaced. Now, here they will not be equispaced. So, their separation will decrease with higher j value. Okay. So, that is the difference one can see, and seeing the spectra in spectrometer, one can say that whether the molecules behaving like a rigid rotator or non-rigid rotator. Okay. So, next we have seen for vibrational spectra of a molecule. So, here also two cases, one is harmonic oscillator. So, their vibration will behave like harmonic oscillator, and another case is anharmonic oscillator. So, in case of a harmonic oscillator, this energy of force is minus k r minus r 0. So, corresponding potential energy will be half k r minus r 0 square. Okay. And their harmonic oscillator, their standard solution from quantum mechanics. So, this E v equal to v plus half h cross omega 0. So, here v is vibrational quantum number. So, in wave number, so this is the omega 0 bar. So, spectral lines, energy of the spectral lines, it seems it is independent of v. So, that means all spectral lines whatever following this selection rule, so all will have the same energy. So, practically we will see just only one spectral lines. So, if it is molecule behaves like harmonic oscillator. Again, it is practically it is different. So, we see its vibration, it is not like harmonic oscillation. So, it is basically anharmonic oscillation, means your stretching and this compression, this is not in same magnitude. So, it is they are in different magnitude. So, in this case this potential energy to feed the experimental data, Morse has given Morse has given suitable potential energy for this anharmonic oscillator, and that is E equal to d 1 minus e to the power minus beta r minus r 0 whole square. So, this called a Morse function, where beta is a constant for a particular molecule and d is the dissociation energy, means it is due to vibration it will this molecule will dissociate to the atom. Okay. So, this bond will breaks basically, and due to this anharmonic oscillation, so this energy terms again it is corrected, okay, by this term. So, V plus half omega E bar. So, here for this omega E is different from the omega 0 bar in case of harmonic oscillator whatever we have seen. So, it is different. Okay. So, V plus half omega E bar minus V plus half square x E omega E bar. X is called anharmonic constant, anharmonicity constant, and yeah. So, if we just rearrange this expression, so this one can write omega E bar 1 minus x E V plus half. So, this whole bracket V plus half. So, this is an anharmonic case, and harmonic case we have seen this energy expression omega 0 bar V plus half. This is the harmonic case. So, if you compare these two, as if this omega 0 bar equal to omega E bar 1 minus x E V plus half. Okay. So, one can consider that that anharmonic oscillator, as if we can consider that it will behave like a harmonic oscillator, but with different frequency, and that frequency depends on the wave number, and that frequency will decrease with steadily increasing of this vibrational quantum number. Okay. So, and in case of anharmonic oscillator, so this selection rule is different, it is not del V equal to plus minus 1. So, other plus minus 2, plus minus 3 etcetera, these are also allowed. Okay. So, so now there are some molecules, so far whatever we have discussed. So, pure rotation of a molecule or pure vibration of a molecule, but in reality there are some molecules where we see this during vibration of the molecule it rotates also. Okay. So, it is called vibrating rotator. So, in case of vibrating rotator, means simultaneous vibration and rotation, due to this what will happen. So, this called vibrating rotator, and corresponding energy here we have written this for this for rotation. So, this is the energy expression. So, higher terms we have neglected, and in this case degeneracy is 2j plus 1. So, population is like this by Boltzmann factor, one can write population and this degeneracy, and we have seen also this maximum population will be at j equal to this. Okay. It depends on temperature, and so this is the for rotation, and for vibration this energy expression is this. Now, for vibrating rotator, so this both energy will be there, rotation as well as vibration, as well as there should be another term, that is a interference term, coupling term between this rotation and vibration. But fortunately, this we can neglect this coupling term, because according to Born, Oppenheimer approximation, since their energy, order of energy of this rotation and vibration is different by a factor of 10 to the power 4. Okay. So, this energy, generally energy of this rotational spectral lines or energy levels, it is 10 to the power minus 1 centimeter inverse, whereas vibrational case it is 10 to the power 3 centimeter inverse. So, huge energy difference between these two systems, rotational and vibration. So, this according to Born Oppenheimer approximation, so they will not interfere. So, one can take the total energy of this vibrating rotator as a sum of this individual energy. Okay. So, E j v equal to E j plus E v. So, E j term one can write, and here we have neglected this higher term, whereas in case of vibration we have taken this both term. So, here reason is that this d value is really very small compared to the b value. Okay. And of course, this anharmonic constant also small, but this we have kept because otherwise we cannot take the selection rule del v equal to plus minus 1 plus minus 2 etc. And that is what it demands, this experimental result demands that this anharmonicity, this term has importance. So, considering the selection rule del v equal to plus minus 1 plus minus 2 and del j equal to plus minus 1, one can show the transition. Okay. So, this vibrational transition between the vibrational level, and then this in each transition this rotational transition also is accompanied. And if you for a particular vibrational transition, say del that v dash to v double dash. So, and there rotational transition from j dash to j double dash. So, if del j equal to say minus 2, minus 1, 0, plus 1, plus 2, although here we have written del j equal to plus 1 and minus 1. So, del j equal to 0 is not allowed, but anyway this whatever spectral lines we see, this we see as a branch. Okay. So, for del following the del j equal to plus 1, whatever the branch of spectral lines we will see, this is called R branch, and following the del j equal to minus 1, whatever the branch of lines we will see, that is called P branch. Okay. And if possible, if it happens that del j equal to 0, if in some cases if for basically not diatomic molecule, for other complicated molecule, if this transition, other transitions occurs other than this del j equal to plus minus 1. So, this series name is given like this. So, this del j equal to 0. So, that lines is called Q lines or Q branch, and similarly S branch and O branch. Okay. So, these are the summary of our earlier study about the vibration and rotation, and now let us continue the discussion of electronic spectroscopy of molecules. So, what we have seen that already we have discussed that this energy levels of spectral of rotational lines, that is basically is 10 to the power minus 1 centimeter, in case of vibration 10 to the power 3 centimeters inverse, and in case of electronic transition, or so this energy is 10 to the power 5 centimeter inverse. So, here again you can see these three rotational, vibrational, electronic transitions, this or their energy levels. So, their magnitude are different in order of in few orders. Okay. So, as per Born-Oppenheimer approximation, again for this electronic transition, total energy del E total equal to, we can write energy change due to electronic transition plus vibration plus rotation. So, total energy due in electronic transition or the spectral energy of the spectral lines in electronic transition, that will be del E total equal to sum of the change of the energy due to the electronic, vibrational as well as rotational. Okay. So, this we have written as per the Born-Oppenheimer approximation. So, here we have to make clear that this that we will get spectral lines, okay, due to the electronic transitions, and in these spectral lines it is not a single line, and that line basically it is composed of many lines. So, it is divided into two parts. One is called core structure of this electronic spectral lines. So, that is due to the vibrational changes, and this again this core structure, again it is this each spectral lines of core structure, again it has fine structure, and this fine structure is due to the rotation of the molecules. Okay. So, we have seen that this pure rotation spectra, because a molecule, and we are seeing this for a particular molecule, it may have rotation, it may have vibration, and it may have this electronic transition. Okay. So, all molecules have rotation, have vibration, and have the electronic transition. Okay. But spectra, whatever if you see in spectroscopy, that spectra we see that some molecules show only rotational spectra, no vibration, no electronic spectra. Some molecules show vibrational spectra accompanied with the rotational spectra, okay, or pure vibration spectra. Some molecules show the electronic spectra, but in case of electronic spectra, all the time this rotational and vibrational spectra are accompanied. Okay. Means this, in case of electronic transition, molecules this vibration of the molecule is active, means infrared active, yes, and rotational spectra is the microwave active. Okay. Although this same molecule, it is not active only for rotational or only for vibrational, okay, if there is no electronic transition. So, here for pure rotation, spectra are shown by the molecules which are possessing the permanent dipole moments. If molecules have permanent dipole moment, only they will show the pure rotational spectra. Okay. If molecules do not have permanent dipole moment, they will not show rotational spectra, pure rotational spectra. Okay. Now, examples are that we have seen that HCl, sodium chloride, carbon monoxide have permanent dipole. So, they are microwave active, and it will give rotational spectra. Fine. Now, in case of so these other molecules like CCl4, CCO2, carbon dioxide, hydrogen molecule, oxygen molecule, chlorine molecule, iodine molecule do not have the permanent dipole moment. They are microwave inactive and they will not show any rotational spectra. Now, in case of vibrational spectra, so in case of to see the vibrational spectra, actually there should be dipole change of dipole moment during motion, during vibration. Okay. There may not be permanent dipole moment, but due to the vibration there will be change of dipole moment. So, in that case that molecule will not show rotational spectra, but it will show the vibrational spectra. So, here we have given example like here HCl, sodium chloride, carbon monoxide. So, as usual they have rotational spectra as well as they will have the vibrational spectra because of the change of the dipole moment due to the motion. Already it has permanent dipole moment, but during the motion there will be change of dipole moment, fluctuation of the dipole moment due to the vibration. So, it will show the vibrational spectra. Okay. So, I think here I have to write not vibration, rotational, not rotational, it should be vibrational, it should be vibrational. Okay. So, but other than that CCl4, CO2, carbon dioxide are infrared active. So, these CCl4, CCO2 they do not have permanent dipole moment, but due to asymmetric stretching and bending exhibit change in the dipole moment, So, this will be infrared active and we will get the vibrational spectra, whereas H2O2, Cl2, I2 iodine molecule. So, they are infrared inactive, means they will not show any vibrational spectra. Okay. So, next if we take this electronic spectra given by which molecules. So, electronic spectra, that is because electronic spectra is are given by all molecules. So, whatever sodium chloride, hydrogen chloride, HCl, carbon monoxide, CCl4, carbon dioxide, H2, O2, Cl2, I2, iodine molecules. Okay. All these molecules will give this electronic spectra, as well as it will give vibrational spectra and rotational spectra, although they do not show the some of them do not show the pure rotational spectra or pure vibrational spectra, but here all will show the rotational and vibrational spectra, and that is because of the electronic transition. And when there will be electronic transition, so it's automatically its distribution of the charge will change, and there will be the fluctuation of the charge, and that is equivalent to that if any fluctuation of the charge. So, it will be active this microwave active and infrared active, and it will show this rotational and vibrational spectra associated with the electronic transition. If there is no electronic transition, so they may not show the rotational vibration, but if any electronic transition is there, so this vibrational and rotational also it will be active, and it will give these spectral lines for rotation and vibration. Okay. So, I will stop here and then I will continue next class. Thank you.